Good morning, all. We will start with problems on strains today. We have learned the concept of strains as well as derived uh, formulations for strain deformation relationships. And once the expressions for strain deformation relationships are obtained, we need to now know how to use those relationships or the average strain deformation relationships, point and average strain deformation relationships to determine strains across elements. Okay. So we will first learn how to solve a few problems. Then probably in the next class we'll learn for transformation of strains. And once we learn transformation of strains, we can use both, find out the strains at a particular orientation and then transform them according to our requirement in different orientations. That should be our objective of this course on the parts of strains. A few of you have a few questions yesterday regarding finite strain as well as on tensors. So I think there are good notes available online itself in the Wikipedia about infinite and finite strain. So I'm just sharing the link related to infinite small strains, but you can have, along with that, you can have links related to finite strain there itself. Okay. Apart from that, I said that I'll share with you a book, which is an online book, which has all details that you might need on solid mechanics. But this is not strength of material. This is a solid mechanics book. So a lot of these parts will not be covered in this course. Our course is very basic course. So this is a book by Alan Bauer, uh, who has written, who has a book also. But this is the soft version of the book, which is available online. So it has all details that might be necessary. Anyone who wants to go with higher courses or advanced courses are related to continuum mechanics or solid mechanics, but it's not necessary for strength of material course. All right, so let's start with the problems. So I have selected a few problems. I know we are expecting that we will cover all the ranges that we have in the concept of strains. Right. So first, let us define. Let us understand that we are on the same pitch, same platform for normal strains, and for average normal strains, as we discussed earlier, that you need to consider a length, a fixed length, and then see how that length has deformed after the load has been applied. Okay, and that the total deformation of that length gives rise to your average normal strain that you have. Now, when you do that, your total deformation has to be divided by a particular, reference length. Now, that reference length can be looked upon in various fashion. One of them is you looked upon using Lagrangian strain formulation, where you look your reference strains to be your original configuration. Okay, so this was your original configuration L0. So your delta by L0 becomes your Lagrangian strain, and if you are looking at the final configuration as your reference configuration, then it becomes delta by L0 plus delta. So that is your Eulerian reference frame. Okay, so generally in solid mechanics we go by Lagrangian strain relationship, especially when we have infinitely small strains. For large strains, you can go either for Euler or for Lagrange, and both will give you different results. Okay, but general formulations for solid mechanics are all dependent on Lagrangian strains. And then we talked about shear strain, and we said that shear strain is nothing but the change in angle from its previous original angle. So if you give a shear stress, or shear load or a moment to this body, what happens, that it will try to bend in this fashion, as we discussed earlier. And therefore this 90-degree angle between the two different faces will not remain 90-degree after deformation. So they will change. If the angle changes to a value which is lesser than 90-degree, then it's a positive shear strain. And if the value changes to, if it changes to something which is greater than 90-degree, which is this case, this is pi by 2 plus something, right? So that gives to negative shear strain. And gamma xy is called engineering shear strain, and which is given by the change in angle from 90-degree. So it is positive when the angle changes, changed angle is lesser than 90, and it is negative when the changed angle is greater than 90. right? We all discussed this, and then we said that there is a point strain that you need to understand, where the length is in a limit going to 0. So you don't consider a finite limit here, a finite length here. What you consider is a very small, infinite small length. So if it is infinite small length, then you get down to derivatives, and then these are the formulations that that defines your strains with respect to deformation. So these are called strain deformation relationships. Please note that it's not it is commonly known, and always it is defined as strain deformations emission relations. So if anybody mentions to you about strain deformation relation, they are mentioning to these values that we are, and that value can be written in a matrix form. This is the engineering strain matrix, and we know that the it is going to be a symmetric matrix. So gamma xy is gamma yx, gamma yz is gamma zy, and gamma zx is gamma xz. Okay, and then you get something called tensorial strains, which is a little bit different from engineering strain. As it goes that the normal strains remain same. So normal tensorial strain is equal to normal engineering strain, but the shear strains, so tensorial shear strain is equal to half the engineering shear strain. So the tensorial shear strain changes by half. So there is a factor here that needs to be applied. This is needed because tensorial shear strength is a mathematical notation. It's a mathematical quantity which needs to follow some mathematical definitions or laws of transformation of second order tensors. You know, uh, so it doesn't follow if it's an engineering format of the strain, but it follows when you have a factor of 2 added to all these shear strengths. So we will see to that in the next class, but this is, please take it as a word of mouth that engineering shear strengths and tensor shear strengths are different, and they are with a factor of 2 only. Right. So let's get into our problems. The first problem is a simpler one. What it's given is, you can read the problem. It gives you that there is a body here. This is a body with many links to it, right? So there is one link at A, there is a plate or something at A, there is a plate or some connection at B, same at C and D. And the forces are applied only at these connections, okay? So we are not interested in forces here because we are not calculating stresses, we are calculating strains. But as you can see, there are forces that are acting in different directions, okay? Now let's say you are not interested in forces or stresses, you are interested in strains, so you put some displacement measuring devices across the elements, all across it. And once you do that, you got the displacement measured, okay? And the displacement of U, let's say at A you put a displacement sensor, at B you put a displacement at C, and D. Let's say there are displacement sensors all across. So there is a displacement sensor here. We call it LDV. Okay, there can be a displacement sensor here, there can be a displacement sensor here, okay, or LVDT, we can use it using LVDT, or we can have laser sensors to measure displacements. Okay, so after you measure, let's say you are measuring with a laser sensor, and once you measured it, you got the values that are given here. So UA has moved from its original position by a negative of 0.01 inch, and UB has moved from its original position to 0.008 inch. Right? Similarly for UC and UD are given. Right? Now you have been told to find out strains at the links between AB, links between BC, and links between CD. Right? How do you find strain? So the strain will be the elongation in AB by its original length. So original lengths are given here, 36, 50, and 36. So you need to find the deformations, how much deformation it has gone through, and then you need to divide it with the original length. So how you are going to find the deformation that is gone through? So displacement at A and displacement at B, you need to subtract them. Right? Once you subtract them, you get the deformation, the displacement at the deformation between A and B, and then you divide by the length of A and B, you get an average strain that is going through between AB. So epsilon, or average strain AB, is given by UB minus UA divided by XB minus XA. Now please note that if this is my positive X direction, B has moved in positive X direction, whereas A, since the force is along this direction, A has moved in negative X axis. So when you put UB as, you have to put UB as 0.008, and you have to put a minus of 0.01, right? Because that has moved in separate direction. So the total elongation that has happened is additional here, right? So UB plus UA in magnitude, they have to be added. So it becomes 0.08, that divided by 36 gives you 0.0005 inch by inch. Okay, right? Okay, similarly, if you look at BC, similarly, if you look at between point BC, your B has moved in the positive direction, your C has moved in negative direction, right? Okay. Now you have to understand that B has moved along this direction, whereas C has moved along this direction. So it's a compression in the body, right? So one side it has moved to the right, the other side it has moved to the left. So the total deformation is going to be, yeah, you know that. So UC minus UB. So you put UC is equal to minus of this, and UB is equal to also minus of 0.08. So you add them up, you get 0.125 divided by 50 was the original length, and then if you divide it, your strain becomes 0.0025 inch by inch. So remember, this inch or meter doesn't matter here, because it's going to be unit free. It's a non-dimensional quantity, so it doesn't matter whether it's inch or meter here. So if you, instead of 50 inch here, if you had 50 meter, you would have got a deformation which is 0.0025 meter. Okay, clear? That's the beauty of strain. That is the beauty of strain, that it is unit free, so you don't have to worry about whether it's in inches or it's in meters or it's in centimeters. You just have to understand that that is the strain, and if you have a length of meter, then that multiplied with length of meter gives you deformation in meters. If you have a length in feet, then that strain multiplied with length in feet will give you deformation in feet, and so forth, so on and so forth. Similarly, for CD section, this section, you understand that UC has moved along this direction, whereas UD has moved along positive direction. So again, they will add up, and once they add up, you get a value of 0.012, and that divided by original length, which is 36, gives you a strain which is 0.0000333 inch by inch. I hope this problem is understood. It's the simplest problem that we can have on normal strains, and we have calculated only average strains here. We have not calculated anything related to point strains here, because to calculate point strains, you need to have functional relationships of u and v with respect to its coordinates. We will see one example later. Right now, let's go to problem 2. Problem 2 gives you a material rubber, which is like this, put up, and this part is fixed, so this part cannot move, and you have given some kind of load on the top part. There is a top plate that is attached, which is rigid, so you're given some kind of load in the top part. If you give shear load here, and let's say under that load, the top part has displaced by a deformation of 0.05 millimeter. Okay, what you have been asked is, you have been asked to find the average shear strain at a point A. So a bar of hard rubber is attached to the rigid bar, which is moved to the right relative to the fixed place A as shown. Okay, so the relative to A, it has moved at 0.5 millimeter. All right, now our job is to find what is the average shear strain. So we are not looking into any kind of other kind of deformations here. So there can be, wait a minute, there can be different, so what I am assuming is the whole thing is uniformly deforming. There is no local deformations, or there is no change in the, so if this line is straight, that remains straight after deformation. They don't change into a different kind of curve after deformation. So that means that the deformation across all through has been uniform. And that will happen only when the system is isotropic and the material is homogeneous. So what we need to find is shear strain. We know that original angle is 90° at this point A. The original angle has been 90°. We need to find how much the angle has changed after deformation, and we subtract it. We get the changed angle, and that is your shear strain. So what we do is, so if the full thing is uniform, then this line has moved 0.5. So this will also move 0.5. That will also move 0.5. Right? All points will move 0.5. So we put a straight line from here. That is here B2. That was earlier here BA, and now that straight line has moved by B dash or B1A, and this distance, as said in the question, is 0.5 millimeter, right? So this is the angle that I need to find out. So this is my gamma. So tan gamma is going to be this pi dash B1B divided by AB. So once you do that, you take a tan inverse and you get 0.005 radian. So your shear strain is 0.005. Remember, when you find shear strain, you cannot put that angle in degrees. You have to put that angle in radians because radian has no unit. So it has to be 0.005 strain. There are few things. Okay, these problems are taken from I'll tell you from where we have taken this problem. We have taken this problem from the notes of Madhukar Wable from Michigan Tech. So if you want, you can go into these notes and get more problems from that book. So he has a note available and a book available in his website. So you can have more problems from his book. He has good question set available. So problem 3 has 3 parts, A, B, and C. All these problems are shear strain problems. You need to find shear strains at various for the various problems that are shown here. I have taken this problem to make sure that you understand the complexity that is involved in calculating shear strains. Okay, the first problem is very simple that we have already done, similar to that. So you need to find the change in angle, right? So this is your, let's say this is your change in angle, and that is going to be gamma. So gamma is going to be, as you know, is at A, it's going to be tan inverse of 0.84 mm is what the length has changed by 350 mm. Okay, that's going to be, and you have to find this in radians, remember. That's going to be your angle, right? So we have learned this already. But what about the next problem, the second problem? The second problem has this part, this length, this length has changed to this one, and both are straight lines. So this is a uniform, right? So this is one angle, and here is another angle. So total reduction in angle is this plus this, right? Okay, so it's going to be gamma at A is going to be tan inverse of 0.0056 divided by 1.4 in radians plus tan inverse of 0.0042 divided by 3 in radians, right? You can find out the angles, find out the values that comes out to be, and that will give you the shear strain that is at point A, right? So that is the angle it has reduced by when it moves to an accurate angle, right? So this is lesser than pi by 2. So this is pi by 2 minus gamma at A. So that the rest is going to be gamma at A. This is also pi by 2 minus gamma at A. Now look at third picture. As you can understand the third picture, the angle has increased from its previous 90-degree undeformed configuration. So it is a negative shear strain, right? Negative shear strain, and the angle here is, you have to find out an angle here. It's in this direction. It's in this direction, right? Okay, so we need to find it out. So gamma at A is going to be, okay, I'll keep some space here. tan inverse of again 0.6 divided by 350, right? 350 in radians plus tan inverse of 0.6 divided by 600 in radians, right? And overall, they will be negative because the angle has increased in both sides. All right. Is that clear? I hope it's clear. So that's how you calculate gamma at A, and therefore your deformed angle is going to be pi by 2, again minus gamma at A. Remember that there is a minus here, so there is a minus here, so that minus and this minus will make it a plus, so it will increase, or its overall angle has, you know, increased more than pi by 2. I hope that's understandable. I'll go to the next problem in that case. This is also a problem of average shear strain. This deals with again, the problem is given that you have a material cross section A, B, C, D. The length of AB is 4 mm and AC is 2 mm, and it's a rectangular cross section or rectangular element, and it has been said that U and V are known. Okay, displacement U and V in x, 1, y direction respectively are measured at various points across the body, and the values for them are given, right? So at UA is given, VA is given, so this point has moved to a new point, let's say, and the new point is here. UA is negative, so it has come this side, and VA is positive, so it's something somewhere here it will start. So A has moved to this point, small a is this point, and then your UB is also negative, VB is also negative. Oh my god, both are negative. So it has come, let's say, somewhere here. I don't know, values may not be correct, but this is your B. So B point has moved both negative sides, right? And UC is both positive. Oh, that's not B, sorry. That's not B. So B is both reduction in length along X as well as reduction in length along Y. So it has become somewhere here. This is B. And what happened to C is both positive. So C has moved above C as well as it has moved to the right. So it's somewhere here. And D is both positive. So somewhere here, let's say. And then this is your deformed and member. Right? This is the deformed member. So the coordinates of the deformed member is given in terms of UA, VA, UB, VB, UC, VC, and UD, VD. So the coordinates are given. You need to find out epsilon XX, epsilon XY, gamma XY. Not difficult, right? We have already understood how to find them, and we know that for finding the normal strain, you need to find a normal strain along X direction for a point A. Okay, at point A they have mentioned, so I need to find it at point A. So I need to see how much this length AB has increased or decreased along X, and that divided by the length, original length along X, will give me strain along X. Then I need to find how this length AC has changed after deformation along Y. Once I know that, I can divide that with the length AC to get the strain along Y. And to find shear strain along A, I need to find how much C has moved with respect to A along X-axis and how much B has moved with respect to A along Y-axis. Y-axis. And then respectively, I have to divide with their lengths along X and Y-axis, and then we can get shear strain. So we have to use the formula that we have derived. So the formula was like this. At A, epsilon XX at A is going to be delta AB by previously whatever AB was there, right? AB. epsilon xx at a, sorry, epsilon yy at a is going to be delta AC by AC. Okay, this is along x, so no, delta AB along x. This is along y. And gamma xy, as we know, sorry for that, gamma xy is going to be delta AB by AC plus delta AC by AB, I think, you know. No, sorry for that. Yeah, sorry, it's not that. It is delta AB along y by delta by AB plus delta AC along x by AC. And this is the formula that we have found out while doing the shear strengths. I don't know where the formulas are. Yes, probably here. So if you can see, it is del u by del x. That means deformation along u, deformation of u along x by x, and gamma xy is del u by del y, del v by del x. Okay, clear? So we'll go there and do these calculations now. So ua minus ub is the deformation of AB along x direction, because u is along x direction, right? So that will this. VB minus VA is deformation of B with respect to x but along y direction. Okay, because V is along y direction. Similarly, UC minus UA is deformation of C along x direction with respect to A. VC minus VA is deformation of C along y direction with respect to A. All right, I'll write them down when I send this notes to you. Now sigma xx is deformation of B with respect to A along x direction by the original length, right? So that comes out to be this one, 0.005 divided by 4, and that is this, 0.00125 millimeter by millimeter. Similarly, yy will be deformation of C along y direction divided by the original length, that was AC. So that's what this is. So you get a value like this. All right. Now shear strain is going to be deformation of B along y direction. That's what I said, right? Deformation of B along y direction, and that will be given by the components of deformation along y direction, right? So that will be VB minus VA, because V is along y direction. Okay, so this is along x, along y, this is along y with respect to its original length, and this is along x with respect to its original length, yc minus y, right? So when you do that, you get gamma xy. You just add them up and you get some value that should be in radian. Okay, that's the angle. So gamma xy has no unit, so there is no radian there. All right, is that clear? Do you need to stop? Do you want me to stop the video and go ahead, or shall I can continue? I have another 2 problems to solve. Okay, let me continue and then we'll have question session. Problem 5, displacement. So here, what happens is you have been given the functional form of u of x. See, so displacement in a quadratic axial element. So these elements are used for finite element. Okay, finite element analysis. So it's, you don't need to know the nitty-gritty of finite element analysis, but assume that this is an axial element. So for example, if you have an axial rod, when you discretize that rod into various small elements, you use axial elements. So one of the axial element is given as 125 x squared minus 3x plus 8 10 to the minus 6 centimeters, and it is valid between 0 to 2 centimeters. Okay, so when I have this, I have been given this function. I have to find epsilon xx at x equal to 1 centimeter. So I have to find a point strain. So note that this I have been asked to find point strain. Okay, this is point strain that has to be found out at x equal to 1 centimeter. So when I exercise my definition at a particular point, when I give that value of the point, I need to find point strain. And point strains are given by the derivative, so epsilon xx is nothing but epsilon xx is du by dx, and u has been given to you. U in the functional form of x is given like this. Therefore, you can find du by dx and put x equal to 1. And if you do that, you can take derivative of this, that will come out to be this, and then put x equal to 1, you get minus 125 10 to the power of 6. So this strain will be written as minus 125 micron. Okay. All right. Now let's go to problem 6. It's a little bit, little bit involved problem for understanding, but it's not very difficult. What I have done is, it's that the figure is given here, longitudinal bar which is hanging, a bar which is hanging. There is a fixed here. So there is a load that is given. Let's say I don't know the load, but I've been asked to find out the strain that is going into the material. Okay. Let's say there is a dead load on it. That means its own self weight, and it has said that epsilon xx, strain is given by k into L minus x. So at any point, epsilon xx, the axial along strain, is given as k. K means a constant into L minus x. So how far it is from the free length. Okay. Let's look at whether this value is given correct or not. Oh God, where is this rubber? Yeah, it's here. So what has been asked is, can you find the deformation of the material, extension of the bar at L? All right, how much it has elongated at L? So I said that I need to see whether this is the value given is correct or not. Okay. At the free end of the material. Okay, at the free end here, what will be the strain? Just think on it. What will be the strain at the free end of the material? Think on that. Yeah, okay. Now let's look at how do you do it. So for me, I have been given epsilon xx, which is nothing but k into L minus x. Now what is deformation? Deformation is du by dx. Deformation is u, and du by dx is given by as epsilon xx. So if I integrate epsilon xx with respect to, so I get du equal to epsilon xx into dx. So if I integrate du, I get epsilon xx dx integration. Let's say between 0 and L. So that means it will give me u at L minus u at 0, right? So if I need to find deformation, I need to integrate the strain. And if I need to find deformation at any point, let's somehow allocation which is x at equal to L3 L by 4, let's say. Then what I'll do integration 0 to 3L by 4 du, which is 0 to 3L by 4 epsilon xx dx. So here I've been asked to find deformation at the end, free end, total extension of the bar. So that means at the free end I have to find deformation, and that will give me the total deformation that the bar has gone through. So I have to integrate between 0 and L. If I do that, so this is what has been done. If you do it, you get this value. But please note, I need to know what is u of 0. Otherwise, I cannot find u of L. So what is u of 0? U of 0, this point is fixed, right? Therefore, deformation at point x equal to 0 is 0. But deformation at x equal to L, then it's given by, just this value in terms of L once you integrate it. So please note, if you know deformation at any point, any fixed point on the body, you can find deformation along any point of the body just by integrating it. But again, I'll tell you, there is a word of caution here that you have 3 deformations. One is along x, one is along y, along z. So u, v, and w. But you have 6 strain components. That means epsilon xx, epsilon yy, epsilon zz, epsilon xy, epsilon yz, epsilon zx. Or if you are looking at 2D, then you have 2 deformations, u and v, along x and y directions respectively, but you have three strain components. One is epsilon xx, epsilon yy, and gamma xy, or epsilon xy, and therefore you cannot directly find it unless I give you a simple problem like this, which is 1D. Direct integration is not going to give you the strain components. You need to satisfy something called strain compatibility conditions. So that should be added up along with your unknown questions, and that will solve the problem. Otherwise, you have more strains, less deformations. Okay,